Introduction. Hey everyone, welcome back to Blueprint to Reality. In today's video, we're diving into a topic that's more relevant than ever: how to design buildings that can withstand extreme heat conditions. As climate change intensifies, many regions are experiencing record-breaking temperatures. This poses a serious challenge for buildings, especially in areas prone to heat waves. But don't worry, we have some smart structural solutions that can help make buildings more resilient to rising temperatures. Thermal mass, the power of heat absorption. The first solution to consider is thermal mass. But what exactly is it? Thermal mass refers to a material's ability to absorb and store heat. In buildings designed for hot climates, materials like concrete, brick, or stone can be used to regulate indoor temperatures. By absorbing heat during the day and releasing it slowly at night, thermal mass can reduce temperature fluctuations. This helps keep interiors cooler during the hottest parts of the day without relying heavily on air conditioning, which saves energy and reduces the building's carbon footprint. Shading strategies. Passive cooling. Next up, let's talk about shading. Strategic shading is a low-cost, passive cooling technique that can make a world of difference in extreme heat. Roof overhangs, awnings, and exterior shading devices like louvers and pergolas can block direct sunlight from hitting the building's windows and walls. By keeping the sun's rays off the building, shading reduces the amount of heat entering the structure. It's simple, yet highly effective. Combining shading with reflective or light-colored materials further minimizes heat absorption, keeping the structure cool from the outside in. Ventilation and airflow. Letting the building breathe. Proper ventilation is another key factor when designing for extreme heat. Buildings in hot climates should allow for natural airflow to circulate cool air through the space and expel hot air. Architects often use techniques like cross-ventilation, where windows on opposite walls are aligned to allow fresh air to flow through. Stack ventilation, which uses height differences to encourage hot air to rise and escape, can also be used to keep interiors cool. Innovative materials. Reflective and heat-resistant. Finally, let's explore some innovative materials. Reflective roof coatings and paints can bounce sunlight away from the building, reducing heat buildup. Insulating materials like aerogels provide superior protection against heat transfer, keeping interiors comfortable. These materials not only protect against extreme heat, but also improve the building's energy efficiency, making them a smart choice for future-proofing structures. Thanks for watching. These are just a few structural solutions that can help buildings withstand extreme heat. If you found this helpful, don't forget to like, subscribe, and share this video. Stay cool, and I'll see you next time on Blueprint to Reality. Welcome to Blueprint to Reality, where we explore groundbreaking ideas in civil engineering and architecture. Today, we're diving into a fascinating sustainable building technique that's gaining momentum around the world: rammed earth structures. Introduction to rammed earth. Rammed earth construction isn't new. It's an ancient building method that's been around for thousands of years. Used in structures from the Great Wall of China to Moroccan Casbahs, rammed earth is a technique that involves compacting layers of damp earth between forms. The result? Strong, thermally efficient, and environmentally friendly walls. Advantages of rammed earth. So, why are we seeing a resurgence of rammed earth today? First off, sustainability. As we face the challenges of climate change, the construction industry is looking for greener alternatives. Rammed earth uses natural, locally sourced materials, reducing the carbon footprint. Unlike concrete or steel, it doesn't require high-energy production processes. Secondly, its thermal properties are a major benefit. Rammed earth walls provide excellent insulation, helping to regulate indoor temperatures naturally. This means reduced energy consumption for heating and cooling. Modern applications and innovations. In recent years, architects and engineers have started to reimagine how rammed earth can fit into modern design. From luxury homes to eco-friendly resorts, rammed earth structures are finding their place in contemporary architecture. Advanced construction techniques and new materials, like stabilizers, are improving the strength and durability of these buildings while maintaining their natural aesthetic. Designers are also experimenting with various pigments and textures, creating visually striking structures that blend seamlessly with their surroundings. Rammed Earth is a perfect blend of ancient wisdom and modern innovation, offering a sustainable, durable, and beautiful building solution. As we move forward in the age of eco-conscious design, this technique may play a key role in reshaping how we think about construction. Thanks for tuning in to Blueprint to Reality. If you're passionate about sustainable design and cutting-edge architecture, don't forget to subscribe and hit the notification bell for more insightful videos. Welcome to Blueprint to Reality. Today we're talking about some of the most infamous cases of engineering gone wrong. From bridges to skyscrapers, engineering failures can have catastrophic consequences. We'll explore 7 famous structural disasters where mistakes in design, construction, or maintenance led to tragedy. These incidents remind us why precision, attention to detail, and adherence to safety standards are crucial in the world of civil engineering. 1. Tacoma Narrows Bridge, USA, 1940. Let's start with the infamous Tacoma Narrows Bridge, nicknamed Galloping Gertie. Built in Washington state, this suspension bridge dramatically collapsed just months after it opened in 1940. Wind-induced vibrations caused the bridge to sway uncontrollably, as captured in now-famous footage. The design overlooked the effects of wind on such a flexible structure. This disaster revolutionized how engineers approach aerodynamics in bridge design, highlighting the importance of accounting for natural forces. 2. Hyatt Regency Walkway Collapse, USA, 1981. Next is the Hyatt Regency Walkway collapse in Kansas City, Missouri, in 1981. During a hotel event, 2 suspended walkways gave way, falling onto a crowded lobby below. This collapse killed 114 people and remains one of the deadliest structural failures in U.S. history. The cause? A change in the original design for the walkway's support rods, which couldn't bear the load. This disaster emphasized the dangers of modifying structural designs without thorough re-evaluation. 3. Ronan Point Tower, UK, 1968. The collapse of Ronan Point, a residential tower in London, occurred just 2 months after it was completed. In 1968, a gas explosion on the 18th floor caused one corner of the building to collapse like a stack of dominoes. The failure exposed the fragility of precast concrete panel construction and poor connections between structural components. This disaster led to stricter regulations on high-rise buildings in the UK and better safety standards for gas installations. 4. Sampoong Department Store, South Korea, 1995. In 1995, the Sampoong Department Store in Seoul collapsed without warning, killing over 500 people. The building's failure was caused by illegal modifications to the original structure, including the removal of support columns and overloading of the rooftop. The disaster was a wake-up call about the dangers of ignoring engineering principles in favor of profit, stressing the importance of strict adherence to structural integrity. 5. Florida International University Bridge Collapse, USA, 2018. In 2018, the pedestrian bridge at Florida International University collapsed just days after its main span was installed, killing 6 people. The collapse occurred due to design flaws in the bridge's tensioning system, which created cracks that went unaddressed. This tragic failure underscored the importance of early detection of structural problems and following protocols during construction. 6. Rana Plaza Factory Collapse, Bangladesh, 2013. The Rana Plaza factory collapse in Bangladesh is one of the deadliest structural failures in history, killing over 1,100 workers in 2013. The building, which housed multiple garment factories, was poorly constructed with substandard materials and unauthorized floors. The collapse revealed the extreme dangers of cutting costs at the expense of safety and led to worldwide scrutiny of building regulations in developing countries. 7. Savar Building Collapse, India, 2017. The Savar Building collapse in India, also known as the Lotus Business Park fire, involved the collapse of an under-construction building due to poor materials and design. This incident highlighted the need for quality control and proper oversight, particularly in fast-growing urban areas where construction standards may be compromised. Each of these disasters demonstrates what can happen when engineering goes wrong, whether through design flaws, cost-cutting, or poor execution. But they've also paved the way for better practices, stricter regulations, and new technologies. Thanks for watching Blueprint to Reality. Be sure to like, subscribe, and hit the notification bell for more content on engineering, design, and the lessons we can learn from past failures. Stay safe, and we'll see you in the next video. Welcome to Blueprint to Reality. Today, we're diving into one of the most impressive feats of engineering, suspension bridges. These towering structures seem to defy gravity, effortlessly hanging between 2 points. But what's the secret behind their strength? The basics of suspension bridges. At first glance, suspension bridges are marvels of simplicity, but don't be fooled. The science keeping them standing is anything but basic. A suspension bridge consists of 3 key parts: the deck, cables, and towers. The deck is the part of the bridge you drive or walk on, but it's not just resting on solid ground. Instead, it's suspended by cables, massive steel ropes that connect the deck to the towering vertical structures on either end, called the towers. These towers hold most of the weight. How suspension works. Now, here's where the physics comes in. Those steel cables are the backbone of the suspension system. When a load like cars, trucks, or even people moves across the bridge, it creates downward force on the deck. The cables take that force and spread it across the entire span of the bridge. They transfer the load to the towers, which then transfer it down into the ground, or foundations, deep beneath the surface. Think of the bridge as a giant hammock. The cables are like the ropes of the hammock, and the deck is like the fabric. The weight on the bridge causes tension in the cables, but the towers act as anchors, keeping everything in balance. Stability and flexibility. An important feature of suspension bridges is that they're designed to be both strong and flexible. In fact, flexibility is crucial. Winds, temperature changes, and even earthquakes can cause the bridge to move slightly. That movement helps it absorb stress instead of breaking. Engineers calculate how much sway a bridge can handle to ensure it stays standing, even in harsh conditions. The cables are made from thousands of smaller steel wires twisted together, allowing them to carry incredible weight and remain flexible enough to handle shifting forces. So the next time you drive over a suspension bridge, take a moment to appreciate the science at work. It's not just concrete and steel, it's an intricate dance of tension, weight distribution, and flexibility. That's the magic that keeps these bridges standing tall and strong. Thanks for tuning in to Blueprint to Reality, and we'll see you next time. Welcome to this brief but important explanation of a critical phenomenon in structural engineering, buckling. You've probably heard of structures collapsing unexpectedly, and in many cases, buckling is the hidden culprit. So, what exactly is buckling? Why does it happen, and how do engineers prevent it? Over the next few minutes, we'll explore these questions to uncover the dangers of buckling and its role in structural failures. What is buckling? Buckling occurs when a structural element, like a column or beam, suddenly bends or twists under compressive stress. Imagine holding a long, thin ruler upright and pressing down gently from the top. At first, it resists the force, but at some point, it bends to the side. This is buckling. In real structures, this can be extremely dangerous. Columns in buildings or bridges are especially vulnerable to buckling when they are subjected to too much weight or force. Why does buckling lead to collapse? Buckling is dangerous because it often happens without warning. When a structure buckles, the load it was carrying can no longer be supported. For example, in a skyscraper, if a column buckles, the entire weight of the building above that point may no longer have the proper support, leading to a rapid and catastrophic collapse. This is why buckling is one of the key failure mechanisms that engineers must consider in their designs, especially for tall buildings and slender structures. Critical load, the tipping point. So, what determines whether or not a structure will buckle? Engineers calculate something called the critical load, which is the maximum load a column or beam can handle before buckling. This depends on several factors, like the material, the length and shape of the element, and how it's supported at both ends. Once the load goes beyond this critical point, even a tiny increase in force can cause sudden failure. That's why understanding critical load is essential for designing structures that can withstand compressive forces. Preventing buckling in structural design. To prevent buckling, engineers reinforce structures by adding bracing, using stronger materials, or making columns thicker to resist compressive forces. Sometimes, Reducing the length of the columns or providing better support at the base can also minimize the risk. By understanding the causes and effects of buckling, engineers can create safer structures that won't fail under unexpected loads. Conclusion. In summary, buckling is a silent but severe threat in structural engineering. When a structure buckles under compressive stress, it loses its ability to support loads, leading to potential collapse. By carefully calculating the critical load and designing to prevent buckling, engineers ensure that buildings, bridges, and other structures remain safe and stable, even under heavy loads. Thanks for listening, and remember, structural safety is all about understanding and preventing failures like buckling.